I'm here at useR 2014 at UCLA with Max Kuhn. Hi, Max.
Good to see you.
So I'm really looking forward to talking to you. I have to admit, when I discovered your famous package, caret, it really seemed to me to be this fantastic fusion of, like you just said off camera, art and science. It seems like you've taken all of this hard-earned, hard-won experience and really codified it into something that allows lots of people to get a real leg up on actually training models and doing all this predictive analytics. Can you talk to me a little bit about your philosophy?
Sure. So, I work mostly in sciences, in early pharmaceutical sciences, and we have a lot of data where we do a lot of modeling. And even before I was in pharmaceuticals, I was in the diagnostic industry, and really there, when we were developing algorithms for instruments, we tried to use as many algorithms as possible. So, we have a lot of scientists we work with. The answer is partial least squares, PLS, no matter what the question is.
Yeah.
And so, we found that didn't work so well. And so when I left that company and went to Pfizer, we had a few, I had a few months really where I didn't have access to much. And so talked to my boss and started working on the package simply so we could just attempt to try other things. Because before that, within R, there's so many different interfaces of things. There's a lot of sort of like syntactical minutia between packages. And so having that package that sort of unifies that and makes it very simple to go between models, that really enabled us to try out a lot of different things. And then you try out things and you gain a lot more experience than you would have otherwise, where you were really, sort of tied down to a couple different models. So it really enabled a lot of creative analysis.
I really, and this is probably a little extreme, but I believe caret is one of R's genuine competitive advantages in the field. I really do. So not only did you clean off the interface for dealing, with the difference between prob and probability and all of those, but you also baked in a lot of methodology. You baked in how to do, training control, how to tune a parameter grid. When you set out, when you had these months, did you realize what a large undertaking it was going to be and how many things it was going to end up involving?
No, not really. I probably wouldn't have done it if I had thought about that. Yeah, and for a while, I think it was about a year before it was released on CRAN. And so we were doing a lot of computational chemistry modeling at the time. And basically that was what drove it. There was probably like a dozen models that we were very interested in, very sort of diverse set of 12 or so. That we initially put in there. And so I have to say, I wish I'd maybe taken another week or two and thought about architecture a little bit more, because it grew over many iterations. So it was the kind of thing where it wasn't a glorified script, but at the same time it was very constrained in a lot of ways. And I wasn't very forward thinking about the package. So it's gone through a couple revolutions where we had to kind of rewrite a bunch of things. So, at the time, we were just trying to get some things done. And then once we thought about putting it on CRAN, that sort of made me step back and say, okay, well, wait a minute. What are the other things people are going to want me to do here? And then we generalized a little bit and over time started generalizing more and more until just last December, I think it was, really baked in, I think, relatively easy functionality to include any sort of pre-processing or modeling that anybody would want to use, as opposed to picking off the menu of what was already there. Yeah.
Well, no, and it does. So it does pre-processing, which I think is a fantastic feature, because not only do you do the pre-processing for the training, but once you've got that caret object, it'll actually do it for all future data as well. So it seems to me like what you're trying to do is you're trying to help people who are starting in the field, or maybe not starting, but a little, have some level of experience, avoid the common pitfalls and mistakes.
Yeah, and that's a big part of it. We've made a lot of those same mistakes, and we want to. I want to say almost like protect people from doing things, because there's a lot in the literature that's just not done very well, but especially in some of the non-statistical journals where there's not much statistical oversight. And so you'll see people sort of using references to say, well, I read this thing where they just repredicted the training set and, they did really well. How come you don't do very well on that? And yeah, I know. And so, we try to avoid, we don't prevent anybody from doing anything, but at least when we do something, we do it under the best circumstances possible. And a good example of that is the feature selection. There's some feature selection routines in there.
Is that the RFE feature?
Yeah, it's a recursive feature elimination. There's another one that's kind of poorly named, SBF, or selection by filter, if you just want to apply a very simple, univariate filter. And the thing about feature selection is, and I've done this, so there are people who would do feature selection, and when they cross-validate the model, they do it within the feature selection. And the cross-validation or the resampling has no idea that features being selected, so it doesn't really include any of the noise or uncertainty due to feature selection, which could be very, very large. And so when we put our methodology in caret, we did it what we think to be the right way, which is you resample and then you do feature selection within that. And it's more computationally taxing, but it will give you much, much more realistic estimates of performance. But we also have the parallel processing in there too, which enables us to, maybe not take so much of a hit time-wise to build models.
So I'm a parallel processing guy. A lot of the stuff that I do is HPC and supercomputing. And one of the things that just blew my mind was when I got to your webpage, and and I was looking through caret, and I got to literally at the end. There's just like, oh, and by the way,
whoops.
And as an additional feature, we will allow you to run these incredibly high-end machine learning algorithms on as many cores as you have.
Yeah.
Is that something? So did R make that easy to do? Did you fight against R?
That was one of the things that developed over time. So early on. So Pfizer uses this grid queuing system called LSF, which is effective, but it's kind of, use a Baltimore term here, it's kind of kludgy to use. It's kind of hard to use if you want to just do something very quick in parallel. And so back then there were only one or two. There's like MPI and maybe and maybe one other way to do parallel processing. So due to the architecture of the package, we had different versions for different parallel processing technologies. And that worked for a while, but support-wise, it was not an easy thing, and it wasn't a very intelligent thing to do. So around that time, this very smart individual, Steve Weston, who was at Revolution Computing, he's really an expert in parallel processing, and we sort of got a sneak peek at the for each package before it was released. And at the time, it didn't really strike me as how powerful it was. But the wonderful thing about that package is he developed really the infrastructure to do things in parallel. Whether you want to or not, you can still run sequentially. And then other people have made bindings essentially to if you want to use multi-core or MPI or whatever technology. So it's a framework for doing parallel processing, being agnostic to the technology used. And that was great for us because it was very easy for us to use. We know Steve pretty well, so we could consult with him when there was any questions, which actually there were none. And then if I use multi-core on the Mac and on Linux.
That's DoMC?
Yeah, DoMC. Yep. And but you don't have to. And so that's one of the things that really matured over time, and we really took advantage of that framework. It was great.
So I'm also a big fan of your book.
Oh, okay.
You've written a book. It's Applied Predictive Modeling.
Yes, with Kjell Johnson. Yes.
And I work in the book industry. Could you do me a favor and talk to me a little bit about how you decided to come about writing this really fantastic work, which is clearly a labor of love?
So yeah, that's funny. So Kjell Johnson and Kjell used to be at Pfizer. He has his own consulting company now, Arbor Analytics, and we used to teach a course on modeling we did it for the American Chemical Society one time. I've done it a couple different places, and I think Kjell did it one time for the American Chemical Society, and a guy named Adrian Schell came up and said, hey, have you ever thought about writing a book? He was with Elsevier, and so that sort of planted the seed. We wrote a proposal, we thought a lot about what we wanted to do, and there's a lot of machine learning books out there, and one of the things that we thought was missing was there was something between the Hasey-Tibshirani-Friedman book, which it's not overly theoretical, but it's a very good theoretical foundation. It doesn't really tell you like how to do things or when maybe you would do one thing and not another. Yeah. And so we love that book, but as a practitioner, it takes a while to figure out, well, geez, when's a good idea to do this or that? The other end of the spectrum is really software books, which are great, but again, there's no intuition about what you should do or what you shouldn't do. And so that was the goal of the book, is we wanted to write something in between. And books don't make a tremendous amount of money, so if you're going to write one, you should do it for something other than money. So we wanted to write one that was really the kind of book where maybe 15 years ago we could pick it up and say, wow, that's all the stuff I kind of want to know. And that was our goal. We used a lot of data sets in there that weren't the standard data sets, just to give a new look at things, and are probably more realistic types of problems people would encounter. So everything we did, every choice we made was built on, number one, having people being able to reproduce what we do, and even extend. There's probably a lot of situations in the book where people can do better than we did, just by trying other things. So we wanted people to be able to do that, but we also wanted to teach them, without being too pedantic, saying, you should do this, then, here. just giving some advice on here's some situations where some things would work, and there's not a lot of that in the literature. So one of the things we did was we took a data set that we had analyzed a great deal in the book and just added random features to it. And for a bunch of different models, seeing what their tolerance was for having noise. Yeah. And that was one thing that we started thinking about, like how do we demonstrate the importance of feature selection, and thought, well geez, we've never sat down and characterized for all these different models, which ones are very susceptible to that, which ones aren't. So it's that sort of thing where we were approaching it really again from a practitioner's standpoint, not only in what we wrote, but what we would like to read, kind of thing.
It's funny that you mentioned the word practitioner, because one of the things I feel that is great about your book is that it really does strike a balance between being like learn caret in 21 days.
Yeah.
And it does have some level of theoretical foundation. It does expect you to think. It's not a copy-paste cargo cult book.
Yeah.
It really does a fantastic job of that. I want to switch topics a little bit just to the R language itself for a second, since we're at useR.
Yeah.
I take it you've been an R developer for a while.
Yeah, for a while.
So if you could talk to me a little bit, I like asking this question. Do you have a favorite feature of R? A thing that you're like, this is the thing that makes R amazing to me?
Yeah, so when I teach R at a couple conferences to people who are not statisticians, there's one particular thing that stands out to me that I actually asked John Chambers if he had known. So this is a feature of the language, and I was very curious because I'd never seen it as a feature in other languages, although I'm not, there probably might be and I wouldn't know. And so that feature is the 3 dots or the ellipses.
Oh.
So basically, if you have function A that calls function B, when you define function A, at the very end of the definition, you could have an argument that is literally 3 dots. And that's not shorthand for there's other stuff here, that's a structural part of the function call. And what that does is you can also, when you call the function B inside of function A, you could put the 3 dots in that function call. And what happens is if you pass an argument to function A that's not one of its arguments, it takes that and recognizes that and says, oh, that must be an argument to something else, and passes the argument down. And so for caret, for example, when we go to train different models, so train is the function call that wraps a lot of different models, but it would not be wise, and we wouldn't even think of listing every possible argument for every possible function that we call later on.
Yeah.
And so, for example, if you want to add some numerical argument to a neural network or something like that, you can pass that directly from train to whatever neural network function. And that was something I'd never seen before. I mean, there's obviously passing arguments is common, but passing arguments in a very informal and flexible way seemed to be just this amazing thing. And I think John said that he knows of other languages that have that now. He didn't say, oh, we were the first people, but he wasn't aware of anybody at the time who was doing that. So if anybody knows different, I'd love to hear, because I just think that's a really cool thing that I had never seen anywhere else.
It's funny that you mentioned training a neural network. One of the things that I have used caret to show off to people is I've been able to show them, look, we can literally train a neural network in less characters than it takes to send a tweet about training a neural network.
That's true, yeah.
And I think that's pretty spectacular. So you've kind of alluded to this. So you had a journey with R at this point. Basically, this is sort of a 2-part question. If somehow we have a time machine and you can go back in time and talk to you when you first started your journey, and and I don't know how you were exposed to it, so you may want to talk a little bit about how you were first exposed to R, and you could grab that guy and go, this is the thing I want you to internalize about the future of your journey, your interaction with this. What would that advice be?
Yeah, so how I came to R. So when I was in graduate school, I was in a biostatistics department. SAS was really the software everybody used. I had one professor. It was a biostat department, but there was a very strong non-clinical statistics thread in that department. And one of the instructors was a person who taught, I think the class was actually called neural networks, but it was really incorporated the bootstrap, neural networks, and what we'd consider, at the time they considered modern data analysis methods, and that used S+.
Okay.
And so that was really my first introduction to the S language. And and after I left and went into industry, we used SAS for a lot of things, but there were other things that were just very much more conducive to the S language would do them much better. And so then I really started to migrate towards S+ more than SAS, and then R came along, and from there I think the first Windows version was like 1.4 or something around there. So that's when I started using it, and so that's how I came to it. And it being so flexible, And the packaging system at the time I felt was much nicer than what S+ had. And so that really, I developed some internal packages for quantum response models and things like that. So that's how I sort of took off on R. What would I do? I think I would try to convince myself to think a bit more.
Okay.
So, the thing is, a lot of statisticians are not trained as software developers or computer scientists. And there's been a lot of talk, there's always a lot of talk about this at useR, because I'll ask people, like John or Dirk or somebody and say, I don't know if your training is in statistics or computer science because you're so good at both of those things. And I find that with a few exceptions, most everybody here are statisticians who, maybe because of their pedigree in their graduate department or the problems they worked on, had some informal or perhaps formal training in computer science. And I did not. I had some, but really the nature of my undergraduate education, sort of coming late into math and statistics during my undergraduate education, I think really, I think if I had started off in those fields, it would have enabled me to have more of a computational science background.
Okay.
And so how you architect functions, thinking ahead about, it wasn't until actually working in jobs that I really started to do that. When people would, we had people in our group that would have to devise databases, and we were always thinking of, well, what are they going to throw at us next?
Sure.
And that really started to bleed into my R development. And it's sort of also, right now with people that are coming out of graduate school, I think this is better, but I think it's pretty, for me, I've noticed that statistics is not often thought of as a computational science.
No, absolutely.
Which sounds like heresy for the group of people that are here.
Sure.
But it's generally true that a lot of statisticians in pharmaceuticals and other places were used to having readily available software to do the things that we want to do. And so we don't think often of, well, geez, if I have to write something, what am I going to do?
Yeah.
How am I going to approach that? And what are the good and bad ways of approaching that? And so thinking of it more as a computational science, I think, would lead people to really focus much more on, the computer science aspects of things. Yeah.
Okay. And I actually don't know, I shouldn't ask a question I don't know the answer to, but, caret is sort of the package that you're most famous for.
Yeah.
Are there any other packages that you've built and deployed that you're proud of?
Oh, absolutely, yeah. So we have a contrast package. Geez, I'm trying to think of the ones I have out there. Two packages that I really like a lot. I wouldn't say I'm proud of them, but it's not something I didn't do all the work here. Is so there's this guy Ross Quinlan, who is one of the forefathers of machine learning, who doesn't really get any press in statistics. He built a completely separate sets of tree-based methodologies, and you very rarely read about them in statistics, but in computer science, machine learning, they're huge. And a couple years ago, and so if you were to ask me what's really missing from R a few years ago, I would have said it's Quinlan's C5O model and Cubist. And so those are models that we used at Pfizer at the command line. They were proprietary, and so we knew that they existed, and we knew they worked really, really well, but they were just not discussed anywhere or even thought of. And so a couple years ago, he open sourced his packages, his C code, and we immediately took those, and we had a lot of familiarity with the Cubist code base, so it wasn't as difficult. But we took those and put them in R, which was a kind of an interesting problem to have to work on, and I think that worked out pretty well. And also, it was a nice. This turned out to be around the time we started writing the book, and it was a situation where Quinlan had published a lot in the late 80s and early 90s on some of these models, but then just stopped publishing. But he was still, as far as I can tell, incrementing the software. So in talking to him a little bit and looking through the source code, I don't know, but my belief is that he would find a place where it would not work and make an improvement, or think about, how do I increase the efficiency of that. So the code base is fantastic. It was written very long ago, so it doesn't look like C code you would find now, but it's fantastic. We've pushed millions of molecules through this C code before we put it into R, and it's very, very robust. And so we were to bring that into R, and we were to go line by line through the C code and figure out exactly what this is doing. So we could look at C45, which was published, and he wrote a book on that, and then look at C50 and sort of see how the changes happen along the way. And it's an interesting sort of approach, because I think a lot of people who especially need to publish I don't know that they would take the same model and increment it sort of silently to make improvements, because there's so much pressure to publish everything you do. So, if you look at other statistical models, you'll find things that are very similar but go under different names. Perhaps because they could publish it, an improvement to a model, but call it something else.
Sure.
And so C5, it seems like is a very, and Cubist too, is really looks to be like a culmination of a bunch of little improvements that happen over time that nobody knew about. So it's kind of like, it's like opening up a treasure chest, and there's gold in there, but actually seeing what's actually inside it was actually pretty fun
that
situation.
Sounds pretty amazing, actually.
Yeah.
So, you just said something that I thought was, you pushed millions of molecules through it at the command line.
Yeah.
So I don't know the nature of your job and what you do. Could you talk a little bit about your workflow, as an R developer, as I guess you're a biostatistician?
Technically I'm a non-clinical statistician.
Non-clinical statistician. Could you talk a little bit about sort of your workflow and what's your day like?
Right, so a non-clinical statistician, it's kind of exactly what it sounds like. We work across a wide variety. There's some, there's just somewhat different phenotypes here. There's like the preclinical statistician, non-clinical, but we're generally the people who work early in discovery, either trying to discover a drug target, what a compound is actually supposed to inhibit or alter in somebody's body. We work on helping develop molecules. We build a lot of models to predict what a compound might do. So, for example, we build a lot of models where we want to predict safety risk. Okay. And so we have whole groups that are designed or there to really to kill molecules, okay, which is an interesting position to be in. There's a lot of lab work that we work with. We help design experiments for people. Some of us work in helping increase the efficiency of the chemical synthesis groups. We have groups that work on formulation. It's an extremely diverse set of people. And we generally don't do the typical statistics that people think of in pharmaceuticals, which would be the clinical trials. Mm-hmm. We often use data from clinical trials, but we're not the people who are designing and analyzing and responsible for those. I worked for many years in computational biology, and then they moved those scientists to a different location. And so right now I work supporting our chemistry groups and another group called PDM. And PDM does many other things, but the thing that I think that in Pfizer people know them the most from is they develop all the screening assays. Okay. And so it's a ton of assay work, a ton of somewhat computational, somewhat very simple models. So my day is basically, we typically juggle 5 or 10 different projects. Sometimes they're very large, sometimes they're small. We sort of live and die by our collaborations with customers. We're not really required anywhere, so we have a lot of labs that we're very collaborative with. And in my group, so my group's about 3 people right now, and we support about 500 or 600 scientists. Oh, wow. Yeah, at different sites too, and so...
That's incredibly leveraged. That's pretty fantastic.
That's a very polite way of putting it, yeah. Yes. And it's good in a lot of ways because, we have no illusions that we'll ever be able to support them all. And, there are some people that, they're just not interested in statistical support. And maybe they need it or maybe they don't, but we have the ability to make, we think, a large impact with people who are really interested in that impact. And so we have a lot of diversity that we'll work with one lab pretty strongly for a month or 2, and then they seem to be where they need to be statistically, and they know what they're doing. We've sort of trained them and acclimated them to the types of data analysis that would be good for them, and then we'll sort of nomadically sort of move on to another lab or revisit another lab that might be doing something different. So yeah, there's a lot of very small experiments, or a lot of very large experiments. There's a lot of experiments that we'll work with them on something for a day or a week. Others that 2 or 3 years. Okay. So it's extremely diverse. You don't know what you're going to be working on next month, really. Cool. Yes.
So is there anything that I haven't covered that you want to talk about?
No, I just would like to say, thanks to you guys, and especially, the conference organizers, and especially to our core and the group. It's astounding to think of how much work gets done to make all this happen, and I think, especially for somebody new to R, and even for somebody like me who's been, with it for a while, it's very easy to sort of, and if you're a package developer, this. It's very easy to sort of take for granted what everybody does. You send a package to CRAN and don't really think about it sometimes, and not realize all the mechanics behind that. So we definitely owe a huge debt to the people who spend most of their time managing everything in R.
Cool. Well, thank you very much.
Thanks a lot.